in this screencast, we lay out some examples of things that we might find important to prove. This is a giant theorem in section 10.1 of your textbook. And the results get proven this way. Your author proves collinearity and then leaves the rest as exercises. I will pick up by proving that isometries preserve betweenness of points, assuming that collinearity has been proven in your text. The others make for nice exercises. There's nothing terribly tough here. To preserve betweenness of points, we need to prove that supposing P, Q, and R are points with Q between P and R, we will show that Q prime is between P prime and R prime. That's what it means to preserve betweenness of points. If one point is between two others before the isometry, the image of that point is between the images of the others after the isometry. By hypothesis, Q is on line PR somewhere. That's what it means for Q to be between P and R. It's got to lie on the line, and PQ plus QR is PR. This is the hypothesis. That's what this means. Well, what do we know about T? We know that T is an isometry, and we know that it preserves collinearity because T is an isometry. Then all the images, the distance between P and Q is the distance between the image of P and the image of Q. The distance between Q and R is the distance between the image of Q and the image of R. And the distance between P and R is the distance between the image of P and the image of R. This is almost enough to show betweenness. What else do we need? We need Q prime to be on the line P prime R prime. But that's done by 1, right? T preserves collinearity, so Q prime is on P prime R prime, so Q prime is between P prime and R prime as needed. All the proofs the rest of the way lay on the fact that this is an isometry and something from up above. That's why they are laying out in this order. It's pretty easy to see some of these things going forward. The real biggie for us in this lesson is the following. If you give me two congruent triangles, then there exists a unique isometry T that puts the one on top of the other. And by unique, here's the deal. There are many paths that lead from here to there, right? You probably did this in high school where there was, hey, here's two figures, come up with a sequence of isometries that puts the one on top of the other. The sequences may be different, but the isometry itself, the composition of those isometries is unique. There exists a unique isometry such that A falls on D, B falls on E, and C falls on F. Furthermore, T is the composition of either 2 or 3 reflections. So here's the rough idea here. We begin by creating line L. And line L is the perpendicular bisector of segment AD. Wherever A and D are in the plane, there's a segment between them. L is the perpendicular bisector of that segment. It fits all the properties of reflection. So the reflection over line L of triangle ABC is triangle DB prime C prime, right? So we note that the reflection in line L of A is D. And so what does that give us? So now A prime is D, C prime is somewhere over here, B prime is somewhere, oh, that is hideous. Oh, golly. So sorry. B prime is somewhere over here, right? You got this triangle like so. So then what do? Well, then there's segment BE, and we come up with the perpendicular bisector of segment BE. Now it could be that B prime E, so sorry. So we draw segment B prime E. If B prime happens to be E, then we just use line DE as this line M. We reflect over line M triangle D B prime C prime. Now D is on this perpendicular bisector, so we're still there. B prime goes to E and C goes to C double prime, right? So for the same reason that A prime is D, B prime is E here. We note that the reflection of B prime is E in line M. So B prime goes to E, A double prime is still D, and C double prime, well, we're there, right? Maybe. If C double prime is F, we're done. If not, reflect in N, where N is the perpendicular bisector of C double prime F, and that takes care of things for the exact same reasons. If C double prime and F are the same point, we're done. If not, we're done with one more reflection. So P is the composition of either 2 or 3 reflections. You never need more than 3. Which may lead some of us to wonder, well, why does it have to be 2? Why can't 1 do the job? What if they're the same triangle to start with? Why can't 0 do the job? Well, yes, sure, but you can reflect over a line and reflect back over a line. So if they were the same isometry to begin with, if they were the same triangle to begin with, then you can reflect over any line and back over that same line and use 2 reflections to get back where you started. And if there was 1 reflection, well, 1 is 3 for the same reason. So the biggie for us today is if you have 2 triangles that are congruent, then 2 or 3 reflections takes one to the other. And that's a nice thing to have in your toolbox. Good, you've put up with way too long a video. Thanks so much.